Hello, in this video I'm going to make some introductory comments on wave-particle duality. And this is one of the many weird and wonderful counterintuitive phenomena that exist inside quantum physics. And we've touched upon it already to some extent, a limited extent, when we've been studying light. We've described light as a wave when we went through our wave section. We went through reflection and refraction, diffraction, interference, polarization. Okay, all of that was in classical physics, but still we had success describing light as a wave. We've also started to describe light as a particle when we looked at the photoelectric effect. So this has already been uncovered, these two different models that describe the behavior of light. Neither of them is a literal description of what light actually is, but both of them have their uses. When we get into quantum physics, first step we're going to take here at looking at this inside quantum physics, we'll see a couple of things. First of all, we'll see that this doesn't just apply to light. In this video, I'll be talking about how wave-particle duality applies to electrons as well. And also, the further you get into your studies of quantum physics, the more you'll develop these models. We're going to move away from the classical descriptions of wave behavior, and we're going to develop new models for describing wave behavior and for describing particle behavior. And this will become more coherent between these two parts of the behavior of light and other particles. Now, as with other parts of classical physics that we've covered previously, we're not throwing all of that away. Snell's law and all those other things that we studied previously in the wave section are still really useful. We just can't use them at the quantum level, but we can still use them if we're in the lab and we're using lenses and prisms and all that sort of thing. That's all fine. That's still useful stuff. Just as Newton's laws of motion are still useful in mechanics, we don't always have to use general relativity. It depends upon the situation. Right, so we've already touched on this with light, as I say, and it was then in 1924 you had this guy Louis de Broglie, and he suggested that this dual nature also could be used to describe the behavior of matter. And he proposed that any particle that has a momentum p, so our usual letter for momentum, has an associated de Broglie wavelength, lambda, equal to the Planck constant divided by that momentum p. And this was confirmed in 1927 when electrons were actually diffracted for the first time in the lab. Now, we know for diffraction you want to have a gap which is similar to the wavelength. We covered this in the wave section. If you've got a wave coming along, this is our classical wavefront coming along, and we've got a gap where the width of the gap is similar to the wavelength of the wave, then you're going to get maximum diffraction effects. So we want to, what situations are we going to see this in? How can we exploit this to actually diffract electrons? So let's look at this then. Say we were going to accelerate an electron. This is how we give electrons momentum normally, in that we get an electron gun. We accelerate the electron through a potential difference. So the energy that we're providing to the electron is E times V. This is our accelerating potential that we've got here, our joules per coulomb, multiplied by the coulombs, the charge on the electron. That's our energy in. That's going to our kinetic energy of the electron. So what momentum are we going to get on this? So we can do the old trick here, multiply both sides by 2m. We're going to have 2mev is m squared v squared, which is the square of the momentum. So the momentum of the electron is going to be the square root of 2mev. So that v is the accelerating potential, not the v of the speed of the electron. So off of this, it doesn't take a lot to get the electrons up to a usable de Broglie wavelength in terms of diffraction. So we only have to get up to say 3 times 10 to the 6 meters per second. This isn't even getting into relativistic speed, so we don't have to worry about that. This is only 1% the speed of light. If we get to that sort of speed, we're getting a de Broglie wavelength of 2.4 times 10 to the minus 10 meters, which admittedly is a short wavelength. It's in X-ray, but this is something we can diffract. And how do we get that sort of speed? We only need about 30 volts as an accelerating potential. So this is very manageable. All we need now is something which has got a gap of around about 2 times 10 to the minus 10 meters. And this is where people use thin slices of, you can get crystals or something like graphite is one which gets used quite a lot. You get a thin slice of graphite, and the spacing between the carbon atoms in the graphite is around about this de Broglie wavelength. This has got a similar spacing. So we fire some electrons at the graphite, and then this is acting like a diffraction grating. We're just doing that all over again. We got multiple slits. You know, if you remember with diffraction gratings, that was our step from going from Young's double slit, where we got 2 slits and interference being created from those 2 slits, to a diffraction grating where we've got hundreds or thousands of these slits. And this is what we're doing here with the graphite. We're setting up thousands of slits and we're firing a wave at it, an electron exhibiting its wave behavior. And we see much the same outcome, except when we've projected this onto something which is going to detect our diffraction pattern. And we can't just look at it because, of course, the wavelength is so much shorter. We need, something that's detecting X-rays, essentially, in order to be able to detect this. But we'll see something similar to when we shine light through a diffraction grating, except the fringes will be about 1,000 times closer together. Because remember, with our, whether it's Young's double slit or whether it's a diffraction grating, the fringe spacing is proportional to the wavelength. And when we were using a diffraction grating with visible light, so we've got a wavelength there of 10 to the minus 7, some multiple of that, whatever it may be, say 4 times 10 to the minus 7, or 6 times 10 to the minus 7, depending on what colour light we've got. Well, that's about 1,000 times longer, isn't it, than what we've got here for this electron. So we're going to have the fringes will be about 1,000 times closer together for the electron diffraction pattern. But still, we are demonstrating the diffraction of electrons. And that's even if we've just got one electron passing at a time. Yeah, even if it's just one electron being fired at the graphite, it will still interfere because it's exhibiting this wave behavior. We've got an electron wave coming towards the graphite, which is passing through multiple slits in inverted commas in the graphite and then interfering with itself. So that's what we're actually seeing, even if it's just one electron. So these waves, these electron waves here, are often referred to as matter waves, but we can see that they're not matter waves in the way that we think of when we're talking about, say, a water wave. In a water wave, we've got loads of water molecules all in contact with each other and all moving around as a system, an oscillating system. Here, this is just one particle exhibiting wave behavior, or you could say is one wave exhibiting particle behavior, depending on how you want to talk about it. We've got wave particle duality. Both of these describe the behavior, and we represent this wave with a wave function. This is a common feature of quantum physics and descriptions in quantum physics, that we get these things called wave functions. So these are functions of space and time. So we'll have our space coordinates, our x, y, z, for our 3 dimensions of space, and we'll have a time coordinate for our dimension of time. And this wave function is describing throughout space and time, we're getting amplitudes of this wave, and the square of the amplitude, so the intensity of the wave, is equal to the probability of the particle being at a particular point in space and time. So we're dealing with probabilities here in space and time. And it's these probabilities that are interfering with each other. So we get one wave function coming into the graphite, saying where the electron is likely to be on this incoming beam. So it could be, which slit is it going through? We've got various probabilities. and then all of these probabilities interfere with each other. We get a new wave function on the other side of the probability of where the electron, if exhibiting particle behavior, where it's going to be and when it is going to be. And that is what is then reflected on the screen when we see the diffraction pattern of the electron on the screen. It's the probability of where it's going to turn up having passed through the graphite. And as I say, this is a key part of quantum physics, these wave functions. There's loads of them that get described in different ways and in different circumstances. So it's a large part of the fairly heavy maths, but it's still, undergraduate maths. So if you study physics at university, you'll be doing this sort of stuff, and you'll be describing these wave functions and going through the maths and various differential equations and such like in order to describe the wave particle nature of these objects. So that's about as much as really I can say about this for our pre-university physics. We can't get into enormous amounts of detail on it all, but at least it's showing, it's opening the door to what you'll be studying in quantum physics at university. And it does, I suppose, introduce the one part of it that we do use in exam questions in pre-university physics of calculating these de Broglie wavelengths and describing how we diffract electrons as well. So these calculations do come up, but they're pretty simple calculations. As we can see, we've got a simple equation here, and we've got simple calculations for accelerating electrons and such like. So they're quite nice ones when they come up in exams, because there isn't that much that can go wrong. But yeah, really interesting part of quantum physics, as all of the quantum physics is really. It's just so counterintuitive. Thinking, well, what on earth is an electron now? Up until now, we've been thinking of it as just a really, really small particle, a small ball, a small sphere, which is flying around all over the place. And now we're talking about describing it as a wave, where we don't exactly know where the particle is. We've just got probabilities of where the particle might be. And we'll see more of this when we go back to looking at atomic energy levels again, because all of that is probability based as well. So yeah, it's really changing the view on, well, what is the nature of reality here? What are these particles? What can we actually get a grip on and say is definite? It's a whole new way of thinking in quantum physics.